Okay, we are going to do percent yield real quick. It is just an extension of what we have been doing already. It's using stoichiometry, it's using mold conversions, and it's calculating limiting reactants. It's all going to get kind of rolled into one thing. The lab for tomorrow, you are going to be given 2 reactants, and you are going to have the math part of it. You're going to perform the reaction, and you're going to determine the percent yield of that reaction. And so we'll be using this formula in your lab activity. To calculate percent yield, yield just means to create or make something. So when we're talking about percent yield, basically what we're trying to figure out is how much can I make? This is particularly important in industry. If you are performing a chemical process to make a product, you want to know what is the maximum amount of this that I can make? How much can I get from this process? How much, if I start with this many reactants, what is my end result going to be? So this is where that comes in. Percent yield is calculated with 2 things. There's something called the actual yield. The actual yield is usually given in the problem. Sometimes it's in a table. But generally, you will read this out. It will be part of the information in the problem that you are solving. The actual yield. This is what we actually made. Tomorrow, when you do the lab, when you take your product up to the scale and put it on there, that is what you actually made. It exists. Okay. The other part of percent yield is called the theoretical yield. This is the max amount that could be produced. So the theoretical yield, this is how much, if everything was perfect and there was no error, no contaminants, the process was flawless. This is how much I theoretically could create. In general, actual and theoretical yields never match. They can get pretty close, but there's human error. There's just, there's only so many ways that we can get close to being perfect. So percent yield is where we're going to figure out what percentage of this is, what are we actually making? Is our process good? You calculate that by saying percent yield is equal to the actual yield over the theoretical yield. And then you, of course, multiply that by 100 to get a percentage. So the actual yield is given in the problem. The theoretical yield, you're going to calculate it. It might be mole to mole, but usually it's mass to mass stoichiometry. And then you are going to determine the percent yield by taking the amount given in the problem, dividing it by the theoretical amount that you calculated, and then multiplying by 100. All right, I am actually going to I'm just going to go through and use the same problems that are in this book. So maybe save you a little bit of handwriting there. If you want to look on to page 293, I'm going to do sample problem 9-8. And if you'd like to snap a picture of that to add to your notes or something, you're welcome to do it. But I figure you'd rather be able to just read it out rather than have to copy all of that down. All right. It says chlorobenzene is based on the production of many important chemicals, such as aspirin, dyes, and disinfectants. One industrial method of preparing chlorobenzene is to react benzene with chlorine, as represented in the following equation. And it gives an equation: C6H6 plus Cl2 plus C6H3 or C6H5Cl plus HCl. And then it starts the problem. It says when 36.8 grams of benzene react with an excess of chlorine, the actual yield is 38.8. What is the percent yield? So this one is a pretty simplified version. Most of them are a little bit more difficult, but let's start easy and work our way up. It tells us right off the bat which one is our limiting reactant. We have 36.8 grams of C6H6. And it tells us that the other one is the excess. So if we're going to do some stoichiometry here, some mass-to-mass stoichiometry, we got to start with our limiting reactant. This problem makes that very easy to find. It tells us the other one is the excess reactant. So I'm going to start with benzene, and then I am going to do stoichiometry in order to determine how much of my product I could theoretically make. And if you look at the problem here, we are going to be looking at C6H5Cl, chlorobenzene. So I am going to do mass to mass here. Step one, when we're doing mass to mass, is to convert our grams of our given to moles of our given. So calculator out. 1 mole of C6H6, grams of C6H6. Calculate this. Uh, 12 times 6 is 72. And then 6 times 1 is 6. So my answer is going to be 78 grams. All right, so I calculated the molar mass. Now I have moles of C6H6 or benzene, and I want to use my mole ratio to go to my new compound. The mole ratio is still found in the balanced chemical equation. So I know I have to have moles of C6H6 on the bottom because those have to match every time. And then I look up in my problem, the coefficient there is a 1. Next, I'm going to see my unknown, the thing I'm trying to get to, which is the chlorobenzene. So I'm going to go to moles of C6H5Cl. And I look in my balanced equation right there on page 293, and the coefficient is 1. If I stopped right now, I'd have moles of chlorobenzene. I don't want moles of chlorobenzene. I want grams. So I am going to convert from moles to grams of this compound. 1 mole of C6H5Cl is equal to some number of grams. So 6 times 12 is 72, plus 5 is 77, plus 35 is 112. So I'm going to do my math here. 36.8 times 112 equals divided by 78. And I get 52.8 grams of C6H5Cl. This is what you just calculated, the theoretical yield. You did mass-to-mass stoichiometry in order to determine what can be created. If everything was perfect, and I started out with 36.8 grams of benzene, the absolute most chlorobenzene that I could create is 52.8 grams. To calculate the percent yield, the percent yield is going to be the actual yield. So you have to look at your problem. It tells us the actual yield of C6H5Cl is 38.8 grams. And then the theoretical yield is what I just calculated, which is 52.8 grams. I'm going to divide those numbers, multiply by 100. 38.8 divided by 52.8 equals times 100. And my answer here, my percent yield, and I like to keep a decimal on my percent yields, but I mean, I probably won't freak out if you don't, but I will pretty consistently, I usually keep a decimal. So that's about 73.5%. And that's your answer. How about it? Okay. Let me see if. All right, flip the page to page 294. And we are, let's do one more together here. It says practice number 1. It says methanol can be produced through the reaction of carbon monoxide and hydrogen in the presence of a catalyst. And it gives you a balanced equation of carbon dioxide plus 2H2 yields CH3OH. Okay. And that's methanol. It says if 75 grams of CO react to produce 68.4 grams of CH3OH, what is the percent yield of the methanol, the CH3OH? So I'm going to just copy this down real quick. I think it'll help us. Oh, snap. All right, all I did was copy down the balanced equation there. Let's look at what has been given to us in the problem. And this is something I have found that is helpful in keeping organized if that's what you're struggling with. If it's not the math part or the stoichiometry part, it's figuring out what you have and where you're trying to go. A lot of times it helps if you label the givens and stuff as part of the reaction so you can see what are reactants and what are products. In this case, it says I have 75 grams of carbon monoxide. So, and then I'm producing 68.4 grams of methanol. What is the percent yield? Well, that means I need to figure out if I have 75 grams of carbon monoxide, theoretically, how much methanol can I make? This is how much I did make. This is my actual yield. Theoretically, how much can I make? And that's where you're going to utilize mass-to-mass stoichiometry. So 75 grams of carbon monoxide. We're going to go from grams of carbon monoxide to moles of carbon monoxide. Once I have moles, I'll be ready for the mole ratio. And the ratio is going to be between what I have and what I'm trying to find. So I have 1 mole of carbon monoxide for every 1 mole of methanol, which is CH3OH. And then want to go from moles of methanol to grams of methanol. So I would do a molar mass again. All right, in this case, and that's how I usually work these out. I usually set it up and then go back in and put in my molar masses. I need grams of carbon monoxide. Carbon is 12, oxygen is 16, giving me a mass of 28. And then I need to find my mass of methanol. So I have 1 carbon, which is 12, 4 oxygen, so that'd be 4. So that's 16 plus 16 of my oxygen, giving me a molar mass of 32. So now I have it all set up, mass to mass. Multiply across the top, 75 times 32 equals, divided by the bottom, which is 28, and I get 85.7 grams. This is my theoretical. This is what I calculated. So now that I have my actual and my theoretical to calculate the percent yield, you are simply going to take the actual, 68.4, divided by the theoretical, 85.7, and you're going to multiply by 100. 68.4 divided by 85.7 equals times 100, and I get a percent yield of 79.8%. Ta-da! Questions? Okay. Let's see. Find you one to do for fun then. Turn back to page 297 real quick. And we're just going to try an easy one. Because this one is like you literally just have to like math. Just calculate 28A. You don't even have to do the theoretical yield. It's given to you. Just see if you can calculate 28A right quick. Shouldn't take you but like a second. So what's the percent yield? 75. Easy peasy. Where it becomes challenging is when I ask you to calculate the theoretical yield first. And most of your problems will have where you have to do that. All right, we're going to, I don't really want to do that one. So I'm going to flip around and go to the back. Okay. That's the lesson part of it. We're going to continue practicing, but let me go ahead and stop this for